When you look at a finished house, it appears perfectly still, but every residential building is engaged in a constant, silent war against gravity. Millions of pounds of dead weight are continuously trying to crush the structure into the earth. All of that weight follows a specific structural path. The load from the roof and the floors channels down through the vertical columns, gathering momentum until it is finally driven deep into the ground below. That creates an immediate physical problem. The earth beneath a construction site is rarely a uniform, solid mass. It is a patchwork of shifting materials, hidden voids, and patches of soft, weak soil. If a vertical column rests on a weak patch of dirt, it will begin to sink faster and deeper than the columns around it. Engineers call this uneven settling differential movement. This wireframe diagram illustrates what happens when a single footing gives way. As one support drops, the rigid frame above it is subjected to immense shearing forces. Walls crack diagonally, slabs fracture, and the structural integrity of the entire home collapses. Standard isolated footings offer no defense against this kind of uneven sinking. Because they sit independent of one another in the soil, one failing support pulls the rest of the house down with it. A heavy building can only survive on unpredictable soil if you strip away that independence. The separate foundation points must be tied together into a single, unyielding system. That unification is achieved using a ground beam. Buried in the trenches, this engineered concrete bridge permanently connects the isolated footings to one another. You will often hear this confused with a plinth beam, but they serve entirely different structural roles. A plinth beam sits above the ground floor to support masonry walls. The ground beam is sunk down at the foundation level, dealing directly with the earth and the primary load transfer. By physically linking the footings, the ground beam forces the building's massive weight to distribute evenly across the soil. If one footing sinks into soft dirt, the beam holds it in place, transferring that load to the surrounding stable footings. Acting as that bridge means the beam itself absorbs brutal physical punishment. The weight of the building pushes down on the center, while the columns push back up at the edges, creating massive bending and shear forces within the beam. To survive those competing forces without snapping in half, the concrete relies on a complex, active internal skeleton. This diagram reveals the internal skeleton, an engineered cage of steel. Thick top and bottom bars are longitudinal reinforcement, providing tensile strength to resist bending under the building's weight. Binding them together are shear stirrups, tightly spaced near columns to fight vertical slicing forces at the supports. This photograph shows the critical beam-column junction. The cages don't simply touch, they overlap using calculated anchorage lengths, weaving together to safely transfer massive force. This blueprint shows the precise cross-sections and elevations required for different walls. Because loads and soil conditions change from project to project, a structural engineer must custom calculate the bar sizes, stirrup spacing, and overall dimensions for every single beam. Relying on arbitrary rules of thumb for foundation steel is a recipe for disaster. The construction team must strictly adhere to the approved bar bending schedule and structural drawings. Even the most perfectly engineered blueprint is worthless if the physical construction on site is flawed. Before a single drop of concrete is poured, the crew must complete a rigorous checklist. They verify the exact beam dimensions, secure cover blocks to keep steel off the raw earth, and lock the formwork tight to prevent leaks. If the concrete is poured poorly, or if the steel rebar is too congested for the mixture to flow properly, the team risks a failure called honeycombing. This leaves large, destructive air pockets in the beam. Without a solid barrier of concrete, groundwater easily breaches those porous pockets. The moment moisture hits the internal steel cage, the rebar begins to aggressively rust and expand, blasting the beam apart from the inside out. Achieving the designed strength requires rigorous compaction with mechanical vibrators, proper chemical curing of the concrete, and absolute adherence to the engineer's specifications. Once the trench is backfilled, a perfectly executed ground beam vanishes underground, never seen again. Yet it remains the permanent, custom-engineered anchor that guarantees the survival of everything built above it.